Hello everyone, let's discuss the computability semester of the Topology and Computability module. First, let's define an unlimited register machine. Let us start by fixing the set of natural numbers to include 0. An unlimited register machine, or URM, consists of an infinite sequence of registers indexed by the positive natural numbers. At any step of a computation, every register Rn contains some natural number lowercase rn. The content of any register can be changed in response to the current instruction in a fixed URM program. Then we move on to the next step in the computation and to the next instruction in the program. Now let's define a program. Program is a finite list I1 to IN of instructions. The instructions come in 4 classes. First, there are 0 instructions. For every n, there is an instruction Zn. It sets Rn to 0, or we can write this as lowercase rn is equal to 0. Second, there are successor instructions. For every n, there is an instruction Sn, which adds 1 to Rn. In other words, it replaces the current content of Rn, lowercase rn, with lowercase rn plus 1. Third, there are transfer instructions. For all m and n, there are instructions T of m and n, which transfer the content of Rm into Rn. In other words, it replaces lowercase rn with lowercase rm. Note that capital Rm is unchanged by this. Fourthly, there are jump instructions. For all m, n, and p, there is an instruction J of m, n, p, which compares the content of Rm and Rn, and if they are equal, it jumps to the instruction Ip, if it exists, and stops the computation if IP does not exist. If they are not equal, we move to the next instruction in the program if there is one, and if there is none, it stops. Now, let's discuss an observation for URM program. Given a URM program P, there is some index n in the natural numbers such that all registers Ri with I greater than or equal to n are left unchanged by P. Then, let's discuss some notation. Let P be a URM program and let A1 to AK be natural numbers. Then P of A1 to AK up arrow means that if A1 to AK followed by infinite zeros is the initial configuration, then P does not stop. Given B in the natural numbers, P of A1 to AK then infinite zeros down arrow B means if A1 to AK followed by infinite zeros is the initial configuration, then P does stop, and when it does stop, the final configuration is B, B2, B3, etc. for some B2, B3, etc. in the natural numbers. Following on, let's define partial function. Given k in the natural numbers with k greater than or equal to 1, we say f from the natural numbers to the k to the natural numbers is a partial function from the natural numbers to the k to the natural numbers if f is a function such that the domain of f is a subset of the naturals to the k and such that f of x bar in the natural numbers for each x bar in the domain of f. Then let's define a total function. A partial function f from the natural numbers to the k to the natural numbers may or may not be defined everywhere on the natural numbers to the k. If it is defined everywhere on the naturals to the k, we say that f is a total function. Next, let's define a computable function. Let k be in the natural numbers with k greater than or equal to 1 and let f from the naturals to the k to the naturals be a partial function. We say f is URM computable, or just computable, if and only if there is a URM program P such that for each A1 to AK in the naturals to the k, first P of A1 to AK up arrow if A1 to AK is not in the domain of f, and second P of A1 to AK down arrow f of A1 to AK if A1 to AK is in the domain of f. In this case, we say P computes f. Next, let's define the characteristic function. Let S be a subset of the naturals to the k be a predicate for some k in the naturals where k is at least 1. The function CS from the naturals to the k to the naturals defined by first CS of x1 to xk equals 1 if x1 to xk is in S, and second CS of x1 to xk equals 0 if x1 to xk is not in S. Then CS is the characteristic function of S. Then let's define decidable set. Given S a subset of the naturals to a k a predicate for some given k in the naturals with k greater than or equal to 1, we say S is decidable, or a decidable predicate, or a decidable subset if and only if CS is computable. Otherwise, we say S is undecidable. Now, let's move on to discuss basic computable functions. We will use them to generate more computable functions. First, let's discuss the 0 function. This is the function 0 from the naturals to the naturals, given as 0 of x equals 0 for all x in the natural numbers. Second, let's discuss the successor function. This is the function s from the naturals to the naturals, given as s of x equals x plus 1 for all x in the natural numbers. Third, let's discuss the projection function. For each naturals greater than or equal to 1 and I such that I is between 1 and n, the projection or coordinate function ui to the n from the naturals to the n to the naturals is given by ui superscript n of x1 to xn equals xi. Now, let's move on to defining the standard form of a program. A program P equaling I1 to IL is in standard form if and only if whenever j of mnp is a jump instruction occurring in P and P is greater than L, then P equals L plus 1. Hence, let's give a remark. Any program P of length L can be changed into a program P' in standard form by replacing every jump instruction jmp such that P is greater than L plus 1 with j of mn L plus 1 in such a way that P and P' have the same effect on any initial configuration. Now, let's relate composition and computable functions. Suppose f from the naturals to the k to the naturals and g from the naturals to the naturals are partial computable functions such that the range of f is a subset of the domain of g. Then the composition function g circ f from the naturals to the k to the naturals, given by g circ f of x bar equals g of f of x bar, is computable. Now, let's define substituting. Let g from the naturals to the n to the naturals and fi from the naturals to the k to the naturals for I from 1 to n be partial functions. A partial function h from the naturals to the k to the naturals is obtained by substituting f1 to fn in g, if and only if the domain of h is the set of tuples x1 to xk in the naturals to the k such that x1 to xk is in the domain of fi I from 1 to n, and such that for every x1 to xk in the domain of h of x1 to xk equals g of f1 of x1 to xk all the way up to fn of x1 to xk. Now, let's relate computable functions and substituting. Let g from the naturals to the n to the naturals and fi from the naturals to the k to the naturals for I from 1 to n be partial computable functions. Let h from the naturals to the k to the naturals be the partial function obtained by substituting f1 to fn in g. Then h is computable. Now, let's give some notation. Given partial functions f and g from the naturals to the k to the naturals, we write f of x1 to xk is approximately equal to g of x1 to xk to mean that, first, the domain of f is equal to the domain of g, and second, f of x1 to xk equals g of x1 to xk for all x1 to xk in the domain of f. Now, let's relate computable functions and recursion. Suppose f from naturals to the n to the naturals and g from naturals to the n plus 1 to the naturals are partial functions. Then there is a unique partial function h from the naturals to the n plus 1 to the naturals such that, first, h of x bar and 0 is approximately equal to f of x bar. Second, for every y in the naturals, h of x bar y plus 1 is approximately g of x bar y h of x bar y. Also, if f and g are total functions, then h is also total, and further, if f and g are computable, then h is also computable. Now, let's discuss bounded sums and bounded products. Suppose f of x bar z is a total function and x bar is equal to x1 to xn, then sf of x bar y is equal to the sum over all z less than y of f of x bar z is given by, first, sf of x bar 0 equals 0, second, sf of x bar y plus 1 is equal to sf x bar y plus f of x bar y. Also, the bounded product of all z less than y of f of x bar z is given by, first, pf of x bar 0 is equal to 1, and second, pf of x bar y plus 1 is equal to pf of x bar y times f of x bar y. Then let's give results for bounded sums and bounded products. If f of x bar z is a total computable function, then the sum of all z less than y of f of x bar z and the product of all z less than y of f of x bar z are also total computable functions. Further, note that the sum of all z less than or equal to y of f of x bar z and the product of all z less than or equal to y of f of x bar z are also total computable functions. Now, let's define the unbounded minimization operator. The unbounded minimization operator, mu z less than y, is read the least z less than y such that if there is no z less than y satisfying the given condition, then the value of mu z less than y is y. Hence, let's give a result for the unbounded minimization operator. If f of x bar z is a total computable function and g of x bar y is defined by g of x bar y is equal to mu z less than y of f of x bar z equals 0, then g is a total computable function. Then let's state the fundamental theorem of arithmetic. If n is a natural number greater than 1, then there exists a unique prime numbers q1 up to qk together with the unique natural numbers a1 to ak greater than or equal to 1, such that n is equal to q1 to the a1 times all the way up to qk to the ak, and we call this the prime factorization of n. Now, let's give a result which follows from this. If n is a natural number, then there exists a prime number q such that q is between n and n factorial plus 1. Hence, let's give results for decidable sets. Let k be greater than or equal to 1. If s is a subset of the naturals to the k and it's a decidable set, then so is the naturals to the k without s. If s the subset of the naturals and t a subset of the naturals to the k are decidable sets, then so is s union t. If s a subset of the naturals to the k and t subset of the naturals to the k are decidable sets, then so is s intersect t. Now let's discuss definition by cases. Suppose f1 to fk from the naturals to the n to the naturals are total computable functions, and p1 to pk are subsets of the naturals to the n which are decidable predicates such that for each x bar in the naturals to the n belongs to exactly one pi. Let g from the naturals to the n to the naturals be the function defined as g of x bar equals fi of x bar if and only if x bar is in pi. Then g is a total computable function. Now let's define unbounded minimization. Let k be a natural number including 0, and let f of x bar y from the naturals to the k plus 1 to the naturals be a partial function. Let mu y of f of x bar y equals 0 be the partial function g with domain the set of all x bar in the naturals to the k such that there is some y in the naturals such that f of x bar y equals 0, such that for every x bar in the domain of g, g of x bar is equal to the minimum y in the naturals such that f of x bar y is equal to 0. Thus, we have the following result for unbounded minimization. Let f of x bar y from the naturals to the k plus 1 to the naturals be a partial computable function. Then mu y of f of x bar y equals 0 is a partial computable function. Now, let's define primitive recursive function. The functions obtained from the basic function, i.e. the zero function, the successor function, and the projections ui superscript n for I from 1 to n, by closure under substitution and recursion are called primitive recursive. Note, there are total URM computable functions which are not primitive recursive. On the other hand, let's define recursive function. The class of URM computable functions is exactly the class of functions obtained from the basic functions by closure under substitution, recursion, and unbounded minimization. These are called recursive functions. Hence, a function is computable if and only if it is recursive. Now, let's move on to defining effective computability. Given m and n in the naturals, the function f from the naturals to the m to the naturals to the n is effectively computable if and only if fi, which is equal to ui superscript n circ f from the naturals to the m to the naturals, is computable for all I from 1 to n. More generally, suppose x and y are sets, and there are f from naturals to the m to x and g from the naturals to the n to y, which are are bijections. Suppose f from x to y is a function. We will say f is effectively computable via f and g if the function g inverse circ f from the naturals to the m to the naturals to the n is computable. Now, let's move on to defining countably infinite. A set x is countably infinite or countable or denumerable if and only if there is a bijection f from the naturals to x. Hence, let's give a result for infinite set. Every infinite subset of the naturals is countably infinite. Also, the real numbers are not countably infinite. Now, let's discuss coding finite sequences. The following sets are countable. First, the naturals times the naturals, or the set of all x, y, where x and y are in the naturals. Second, the union of all k in the naturals of the positive naturals to the k. Now, let's discuss some notation. Let I denote the set of all URM instructions. Let P denote the set of all URM program. Hence, let's give a result. We have that I and P are countably infinite. Now, let's define the Gödel number. Let gamma from P to the naturals be a bijection. Then, if P is a URM program, then gamma of P is the Gödel number of P. Now, let's give an important result. There are total functions f from the naturals to the naturals which are not computable. Now, let's move on to giving some notation. Given n in the naturals, let phi sub n of x denote the partial function phi sub n of x from the naturals to the naturals computed by the program with Gödel number n. In other words, is the program the inverse of gamma of n. Hence, given n, phi sub n of x is the unique function with domain wn equal to the set of all a in the naturals such that p stops on input a followed by infinite zeros, such that for every a in Wn, phi sub n of a equals b if and only p of a down arrow b. Also, given n in the naturals, let Wn equal the domain of phi n of x and let En equal the range of phi n of x. Hence, we get the following result. Let f from the naturals to the naturals be the function defined by, first, f of x equals 1 if x is in Wx, second, f of x equals 0 if x is not in W of x, then f is not computable. Next, let's give some notation. Let n be a positive natural number and let e be a natural number. Then psi sub e of, in brackets, n of x1 to xn is the partial function of n variables computed by the program with Gödel number e. So psi sub e superscript in brackets 1 of x is just phi sub e of x. Now let's define the universal computable function. Let n be a positive natural number. The universal computable function of n variables, denoted psi sub u superscript in brackets n, is the function of n plus 1 variables given by psi sub u superscript in brackets n of e x1 to xn is approximately equal to psi sub e of, in brackets, n of x1 to xn. Hence, we get the following result. For each positive natural number n, psi sub u superscript in brackets n is computable. Now, let's define a universal program. A program computing psi sub u superscript in brackets n is called a universal program for n variable computable function. Now, let's discuss a useful result. Let g be a total function given by, first, g of x is equal to 1 if phi sub x is total. Second, g of x is equal to 0 otherwise. Then g is not computable. Also, let's give another useful result. There is some L in the natural numbers such that for any computable function of one variable can be computed using a URM program involving only registers Ri with I less than or equal to L. Now, let's move on to defining Turing machines. A Turing machine consists of a two-way infinite paper tape divided into cells, each one of which contains one symbol from within a given finite alphabet consisting of symbols S0, which is blank, up to Sm. There is also a reading head which looks at one cell at a time and which, at every step of the computation, can move one position to the left or to the right along the tape, or not move at all. The reading head is always in one of a finite number of states Q1 to Qr. The operation of the machine is determined by a finite set S of instructions, called the specification of the machine, each one of which is a tuple of the form Qi Sj Xk Ql. The instruction is interpreted if in state Qi and viewing symbol Sj, perform action xk and change to state ql. The possibilities for xk are first R, which means move one cell to the right, second L, which means move one cell to the left, or third sk, which means erase the existing symbol and write sk. For the machine to be deterministic, for each possible qi_sj, there must be at most one instruction of the form qi_sj** in script s, the set of all instruction. The machine will stop if there is no instruction telling it what to do next. Hence, let's state a result for Turing machines. A Turing machine is completely determined by its alphabet, its sets of states, and its specification. Now, let's discuss using a Turing machine to compute a function. A Turing machine computes the partial function f from naturals to the naturals if and only if given an input consisting of tape with x+1 consecutive ones and blanks elsewhere, and starting with the reading head on the first one. The computation stops if and only if x is in the domain of f, and when it does stop, the tape contains exactly f of x+1 many consecutive ones and blanks elsewhere. Note that in this definition, the input number x is represented by x+1 ones, thus 0 is represented by 1, 1. A Turing machine computes the partial function f from the naturals to the k to the naturals for k greater than or equal to 1, if and only if given an input consisting of tape with k blocks of ones, any two consecutive of which are separated by exactly one blank cell, such that the ith block contains exactly xi+1 ones and contains blank cells elsewhere, the computation stops if and only if x1 to xk is in the domain of f, and when it does stop, tape contains exactly f of x1 to xk plus 1 many consecutive ones and blank cells elsewhere. Now let's give an important result for Turing machines. Let Tc denote the class of functions computable by a Turing machine. Then Tc is exactly the class of URM computable functions. Now let's give results for primitive recursive functions. All primitive recursive functions are total. Also, there is a decidable set S in the naturals such that first, for every n in S, phi sub n of x is a primitive recursive function. Second, for every primitive recursive function f, there is some n in S such that f equals phi n of x. Now let's define being eventually dominating. Given functions f and g from the naturals to the naturals, let us say g eventually dominates f if there is some n in the naturals such that f of m is less than g of m for all m greater than or equal to n. We write f less than star g. Hence, let's give a result for eventually dominating function. Given any sequence fn with n in the naturals of functions from the naturals to the naturals, there is a function g from the naturals to the naturals such that fn is less than star g for each n. Also, there is a total function g from the naturals to the naturals such that f is less than star g for every primitive recursive function f. Now, let's state the Church-Turing thesis. It says a partial function f from the naturals to the k to the naturals is computable, in the sense of there being an algorithm computing it, if and only if it is URM computable. Note, this is not a mathematical statement. Hence, let's give reasons why the Church-Turing thesis seems reasonable. First, Turing machines were devised precisely with the purpose of modelling the notion of arbitrary algorithms as given by Turing's analysis. Second, the class C of URM computable functions can be characterized in several different ways. And third, no other reasonable alternatives of computability have been offered. And, as ever, thank you for watching.